Okay, let's talk about air resistance. Now, air resistance is a type of drag. It's a type of friction. Um, it's it's a type of friction that involves moving through some type of fluid, either a liquid or a gas. It could be either one. And the key thing to understand is, since it's like a frictional force, but it's a frictional force that depends upon the velocity. So the force of the drag is going to be proportional to some constant times v. Now it can get more complicated, and we won't go in this class that far on it. It could also be that the force drag is proportional to some constant times v squared. That's not really important, and it can be in different cases, different ways. Here's the key thing to understand. Out of air resistance comes the concept of terminal velocity. Terminal velocity means that your speed is not changing anymore. So what happens if you have a skydiver that jumps out of an airplane? They have mg acting down, and what they have is the drag force acting up. But since the drag force depends upon velocity, what's going to happen as they fall faster, the drag force gets bigger. So what happens is, as they fall, so let's say that's after 1 second, maybe after 2 seconds I have something like that. Now FD is bigger. MG is still winning, so there's still a net force. At some point in time, FD is equal to mg. At that point in time, the A is equal to 0, the sum of the forces equals 0, force drag is equal to mg. At that point in time, you have terminal velocity. Now, if I was to look at that, let's take a look at what that would be. For example, if I say that F drag is equal to mg, and I said F drag is equal to some constant times velocity, and I'm going to call this terminal velocity. I want to calculate what that terminal velocity is, at least mathematically. I then say that's equal to m times g. Well, now I can see that velocity terminal is going to equal mg divided by b. So now I have some constant. Now you'd have to know what that constant was, and in this class we won't go that far. But perhaps later you will, as you go on in your love of science. If you have it, let's take a look at an acceleration versus time graph. Well, we know that when we start falling, we start with an initial acceleration of g. But here's the thing with when you bring drag into it, when you bring air resistance into it, is the fact that the g is going to change. Quite often we're told to ignore air. The AP level, we're not always going to ignore air. So what's going to happen is that's going to approach it asymptotically, and at some point out here, that would be our terminal speed. Okay, let's take a look. Well, let's now go, if we have an acceleration time graph, let's look at velocity time, because that simply makes sense. We've talked about these graphs a lot, and we know that there's some upper limit to how fast you go, and that upper limit is going to be vt. So that's kind of a dotted line. That's kind of an asymptote that you're going to approach, and what's going to happen is the speed is going to do this. It's going to level off and approach that vt at some point in time. No longer do we have the perfect straight lines that we were talking about earlier. Remember, it's the area under the curve, and the area under the curve of the top curve keeps changing. So therefore the speed is changing. Now, for y versus t, in other words, I'm talking about y is the distance in this direction. So it's essentially the up and down distance. Well, what's going to happen now is you are going to accelerate. So you're going to have a parabola, the 1/2 AT squared. Now your A is going to be changing, so it's not going to be a perfect parabola. Once you reach terminal velocity, it's a linear speed. So out here, this is linear. That means your velocity is constant, your A is equal to 0. Those points should all about line up when you put them together. Just something to think about with air resistance. You're going to see questions with it. So reason your way through it, and I hope this helped.